Hi, welcome to the final video of Unit 6. Again, remember, Unit 6 is a very short unit, right? There's probably not going to be a lot on the exam for centered around this, but they do like free response questions with this simple harmonic motion, okay? So in this video, we're going to focus on energy of a simple harmonic oscillator. The good thing is we had a whole unit on this, right? Unit 4 was that WEP unit, work, energy, power. So some of the questions that you may have already done in Unit 4 are centered around simple harmonic oscillators. So we're just kind of formalizing what is happening, right? So objects that undergo simple harmonic motion will follow conservation of energy. So the change, right, we're going to change gravitational potential energy for a pendulum and elastic potential energy for a mass spring system to kinetic energy and other forms of energy, okay? One of the things, though, that is added here is graphing, right? So graphs will help us visualize data. And there's two graphs that you're really going to see, okay? The first graph is this one with like the sinusoidal look to it, right? The sine curve look to it. So this is an energy, right, versus time graph, okay? So it's not marked, but the axis, the y-axis is energy. And so what you can see here, it tells you that the red is kinetic and the green is spring potential energy. It says KE and SPE. And that blue line that goes right across the top, that's the total energy. So notice that, you know, green plus red gives you the blue anywhere along the way, right? So green plus red, blue, green plus red, blue. Okay, now we go over to the other side. This is an energy versus position graph. Okay, and so it's only going to go back and forth here because, this is for a spring because I can see right here 1/2 ky squared. Okay, because it's going to go back and forth, back and forth, back and forth, right? And so it's only going to bounce back and forth between negative y and positive y. Okay, so you can see it's marked. The green is potential energy. The blue is the KE, but the red line going across the top is mechanical energy. Okay, and so this kind of shows you that here. But again, they'll follow the rules. E before equals E after. So K before plus UG before plus US before equals K after plus UG after plus US after, right? And so typically what will happen is this will be 0 and you have to decide what kind of oscillator do I have, right? And then you're going to look for this and these will end up being 0, right? So you're going to have something along the lines of square root of 2gh, square root of kx squared over m, right? Something along those lines for the kinetic energy or to find the speed at the end, okay? Sometimes you'll see, especially for elastic, so the energy for that's involving a spring will be 1/2 Ka squared. Let me move that. So the energy, right, for in a spring system will be set by 1/2 Ka squared, and for a pendulum, it's actually set for mgh. Okay. And we'll solve for that H piece, or in fact, this is what you guys need to do. You need to write this equation down. I'm sure a teacher will show you how to get to it. But this is how you find the height that is pulled back, especially if they give you an angle with a pendulum. Okay, so let's look at some examples, right? In fact, we're going to do it right off the bat. So H equals L minus L cosine theta. So you have a pendulum of length 1.5. Bob has a mass of 0.100. Displays 10 degrees from the vertical and released. What is the total mechanical energy of the system? And then what is the speed of the pendulum at the bottom, right? All right, and so how do we find this? So the first thing we need to do is how far did we pull it back based on that 10-degree angle, right? And so we're going to have 1.5 minus 1.5 cosine 10, and that's going to give us a height of 0.023 meters. So you don't pull it back right far. You don't pull it back about a couple centimeters. In fact, let me confirm that number because I could have made a simple mistake. So I have 1.5 minus 1.5 cosine 10. Yep, that's right, 0.023 meters. And so the energy for the system is going to be simply mgh, or 0.100 times 9.81 times 0.023. Okay, and then so the energy of the system is approximately 0.023 joules. Okay, and why is that? Because this is basically 10 times 1/10 is 1, right? And what's the only thing left there is that 0.023. Okay, so now let's find the speed, right? So the second part says, what is the speed of the pendulum as the bob passes its lowest point of motion? So what that means is all that potential energy at the beginning has now been converted to kinetic energy at this point. So the m's would cancel out, and you end up with that famous square root of 2gh. Right? Or you can simply say that, that 0.23 is equal to 1/2 mv squared. You can do that as well. Okay? So we have square root of 2 times 9.81 times 0.023. And so at the bottom of the swing, this pendulum is moving at 0.672 meters per second. And now to advance a little bit, there may be a third part to this question where it says, hey, where is the pendulum located? At what height is it located when it's moving at half the speed or a quarter of the speed, right? And so you just keep applying conservation of energy, right? That's what this topic is about, conservation of energy. So now let's look at a mass spring system. So you have a 0.6 kilogram mass at the end of a spring vibrating three times per second with an amplitude of 0.13 meters. Determine the velocity when it passes the equilibrium point, the velocity when it is 0.10 meters from equilibrium, and then the total energy of the system. Okay? So this number right here, this 3 times 10, or 3 times per second, that's actually our frequency, which will lead us to the period, which leads us back to the spring constant. So that's the first thing that we're going to look for, is to determine the spring constant. And so we're going to start with the equation T equals 2 pi square root of m over k. And we're going to solve this for k, which is going to be 4 pi squared m over t squared. And so you plug in the numbers. K equals 4 pi squared times 0.60 divided by, so this is a frequency, so that's 3 hertz is 1 over t, so it tells us that t is 0.33 seconds. Right, or 1/3. And so that tells us that we have a K value of 218 newtons per meter. So we're actually going to work this problem backwards, right? Because we have enough of the information now to find, right? In fact, we're going to find this one first, and then you can pick your own adventure. Which one do you want to do first? Do you want to do when it's 0.13 meters from equilibrium, or do you want to do when it's at the equilibrium point, right? Whichever one you want to do. So remember, the energy for the system is set by the equation 1/2 Ka squared. And this is why we needed K, right? And so we're going to do 1/2 times 218 times A, which it tells us right here our maximum amplitude is 0.13. And so the energy for the system is going to be equal to 1.84 joules. And so now we can finish off our problem here. Okay, so let's do the first problem, or the first part, the first question. And what is the velocity when it passes the equilibrium point? So we know at equilibrium it only has kinetic energy, right? And we solve for the total energy of the system of 1.84. So V is going to be 2 times E over M, and we take the square root of that. So we say 2 times 1.84 divided by 0.60, and that'll give us the speed at the equilibrium point, and that will give us a value of 2.48 meters per second. Okay, so that would be when it's at its equilibrium position. And equilibrium position for a spring just means it's in its its natural state. Okay, now 0.10 meters from equilibrium. Well, that's not quite out to the maximum amplitude because that's at 0.13. Okay, but we know that that's going to be the sum of K plus US. So it's going to be 1/2 mv squared plus 1/2 kx squared, and that's going to equal E. And so let's do a little bit of algebra here. So we're going to multiply everything by 2. So you get 2E equals mv squared plus kx squared. Subtract kx squared. And so you end up with 2E minus kx squared equals mv squared. Divide everything by m. And so you end up with v squared equals 2e minus kx squared over m. And then the final step, take the square root of both sides. And so your speed will be given by v equals the square root of 2e minus kx squared over m. And so that would be the square root of 2 times 2.48 minus 218 times 0.10 squared over 0.60. Okay, and that will give us a velocity of 1.58, if I can read my handwriting correctly. So let me just do that real quick. So 2 times 2.48 minus k, so 218 times 0.1 squared divided by 0.60, and the square root of that. Apparently it's not 1.58. Apparently it's going to be, oh, I put the wrong number in. I apologize. Because our energy is not 2.48, that's our speed at equilibrium. Okay, divided by 0.6, square root of that. So yes, it is 1.58 meters per second. Okay. All right, so short, quick unit. That's the end of the unit. So the only thing left from here is rotation. Okay, so the rotation is the last unit.